How are you guys? Welcome to Form 1 mathematics lesson, and today we are going to look at sets. So we are going to start by defining a set. According to the definition that I have here, a set is a collection of well-defined objects or elements. This is a simple definition of a set, and it's straightforward. So as long as we have objects that have something in common, which are well defined, they can make up a set. Usually, a set is represented using capital letters, and normally we use curly brackets to represent a set. I'm going to give you an example of a set which is a collection of well-defined elements. The first example that comes into my mind is my family. My family is a set. What each member of my family has in common is that they are members of the same family. So I'm going to use F to represent this family. So I have Joe. Let's say Joe is my father. Maria is my mother. My sister, Kimberly. Myself, Vincent, and my young brother, Donald. So this is a set. So you can consider your family to be a set. Let's look at other examples of sets. Let's consider numbers or numbers which are less than 10. That's a set, and I'm going to call that set n. So I use capital letter N is equals to 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. We are not going to include 10 because 10 is not less than 10. So n is a set of whole numbers which are less than 10. So this is how we present it. So I need you to notice that every member of a set is distinguished from each other using a comma. So if you miss, suppose if you miss this comma, one might read this element as 23. So you should make sure that every element of the set is distinguished from each other using a comma. Now let's look at another set. Another set that I can think of are a set of fruits which are served at my former school. So I'm going to present this one using an F. So we used to get bananas, apples, orange, grapes, and pineapples. So this is a set because every element of this set is well defined. A set can also constitute of letters. So we are going to present another set using letters. Let's say from A to F. So this set we have A, we have B, we have C, we have D, we have E, and F. This is a set on its own. Another set that we might consider can be brands of laptops. So I'm going to use B to represent this set. So B is equals to, we have HP, we have Lenovo, we have Acer, we have Samsung, and there is Dell. This list is not exhaustive, but these are the brands that I can think of at the moment, and they make up a set. A set can also constitute of locations. So I'm going to use L to represent locations. We have Harare, we have Bulawayo, we have Gweru, we have Mutare. We can say these are cities. Mutare, and we have Vic Falls. So all these sets we have given are different types of sets which are unique in their own way. But the most important thing is that a set is a collection of well-defined objects. So, using what we have done so far, you should be ready to do the first exercise that we have for this topic. So I want you to look at this exercise, do it in your own time. If there are any challenges, I will be happy to assist. So the next section that we are going to look at are subsets. A subset is a set whose elements are all contained in another set. So let's suppose A is a set of numbers which are less than 10. So A, we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. We are not going to include 10. And let's suppose D is a set of outcomes of throwing a dice. So if you throw a 6-sided dice, you can either get 1, 2, 3, 4, 5, or 6. So here we can see that D is a subset of A. All the elements that are in D are also found in A. So a subset is a set whose elements are all contained in another set. So this takes us to our next example, where we will be considering the set. So in this case, this is our universal set. A universal set is a set of all elements under consideration. Here, our universal set consists of 2 elements. So this is the sign for universal set. So this one is equals to apple, orange. So the subsets of this universal set will first define the singletons. A singleton is a set which contains only one element. So we have apple, and we have orange. And we have the universal set is also a subset of the universal set. It sounds funny, but it makes sense. So apple, orange, which is the universal set, and we also have an empty set. An empty set is always a subset of the universal set. Let's look at our next example, where we will be considering a set with 3 elements. So in this case, our universal set is equals to 1, 2, and 3. So the subsets of this set, we have this set, the singletons, so we have 3 singletons, and as well we have sets which contains 2 elements, which are 1 and 2. We have 1 and 3, and we have 2 and 3. The next set that we are going to look at is the universal set. 1, 2, 3, and an empty set. We can use empty curly brackets to present an empty set. So you can either write this way or we can write it this way, but I normally prefer the latter one. So a set which contains 3 elements is 1, 2, 3, 4, 5, 6, 7, 8. subsets. So the universal set 1, 2, 3 has 8 subsets. Now, on our third example on subsets, we are going to consider a set with 4 elements. So the universal set under consideration is A, B, C, and D. So again, it's usually easier to start with the singletons. So we have A, we have B, we have C, and we have D. And we go on to the pairs. So we have A and B. We have A and C. We have A and D. We have B and C. We have B and D. Then we have C and D. So sets which contains 2 elements, we have 1, 2, 3, 4, 5, 6. Okay, that's fine. And on the sets that contains 3 elements, we have A, B, and C. We have another set, B, C, and D. We have another set, B, A, and D. And the fourth one is C, A, and D. So the sets, the subsets which contains 3 elements, we have 4 of them, and on top of this one we have the universal set A, B, C, and D, and we also have an empty set. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So every set which contains 4 elements have what did I got? Let me count again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So it has 16 subsets. So with this, you must be ready to do exercise 2. We have done almost everything. It's just a change in structure. I encourage you to go through these exercises, and if there are any questions, feel free to ask. The next thing that I want us to look at is the section union and intersection. The union of 2 sets is a set which includes all elements of the two sets. If A and B are two sets, the union of A and B is given by A union B. So this one is a combination of the elements which are found in both A and B. So let's look at this example. A is equals to 3, 5, 6, 8, and 9. And B is equals to 2, 3, 4, and 5. So A union B is equals to, it's just a combination, so we have 3, so I'm just going to take all the elements in A. So we have 3, 5, 6, 8, and 9. And now I'm considering elements in set B. So we have 2, 3. I'm not going to put 3 because 3 is already presented, or it's already in the set, so I don't need to do a replication again. So I include 4, 5. There's no need to include 5 because 5 is already in. So this is a set of A union B. So it's up to you to put these elements in ascending order, but it's not mandatory. So we have 2, we have 3, we have 4, we have 5, we have 6, we have 8, and we have 9. So I've put the elements in ascending order, although it's not mandatory for you to do. Now, an intersection. The intersection of two sets is a set which includes elements common in both sets. So if A and B are two sets, the intersection of A and B is given by A intersection B. So let's consider our A to be, we are now looking at our second example. A, we have 3, 5, 6, 8, and 9. And B, we have 2, 3, 4, and 5. So now we need to consider elements which are common in both A and B. So A intersection B is equal to, we will notice that 3 is common in A and in B. And as well 5 is common in A and B. And there is no any other element which is common in both sets. So this is our A intersection B. So the number of elements in A intersection B is equal to 2. And here the number of elements in A union B is equal to 1, 2, 3, 4, 5, 6, 7. We have 7 elements. Let's consider another example. If A is equals to H I S T O R Y and B is equal to E N G L I S H A union B is given by. So again, I will first consider the elements of set A. So we have H I S T O R Y. Then I also add E. I'll also add N. I'll also add G. I'll also add L. There's no need for me to add I because it's already in. S is already in. H is already in. So I close my curly bracket, and this set is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. It has 11 elements. A intersection B is given by, now we were looking at elements which are common in both sets. So we have H, which is common, so we put H in here. We have I, which is common, we put I here. We have S, which is common, we put S here. Then let's check if there is anything else. T is not common, O is not common, R is not common, Y is not common. So this set is composed of 3 elements. So the number of elements in A intersection B is equals to 3. I will leave example 4 as your homework. But let me do half of it. The provinces that we have in Zimbabwe. So P is equals to, we have Harare, we have Bulawayo, we have Manicaland, we have Masvingo, we have Midlands, we have Marsh, Mashonaland Central, we have Mashonaland West, we have Mashonaland East, we have Matabeleland North, and we have Matabeleland South. So you need to find the cities and then find the intersection, which is P intersection C. So we will look at our third exercise, which is also composed of very simple questions if you consider the discussion that we had so far. So it's a very simple exercise. Again, I will assist you with solutions for that. Now, let's suppose our universal set is made up of numbers between 0 and 20. So the universal set here is equals to 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20. So this is our universal set. And O is the set of odd numbers. Odd numbers are numbers that leaves a remainder when we divide such a number by 2. So these numbers are, we have 1, we have 3, 5, 7, 9, 11, 13, 15, 17, and 19. So they are supposed to be 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then we are going to do the universal set. So this is the sign for the universal set. So everything else which doesn't fall in set O, which is not an odd number, falls outside but inside the universal set. So we have 0, 2, 4, 6, 8, 10, 12, 14, 16, 18, and 20. So this is a Venn diagram. The odd numbers are inside the circle, and numbers which are not odd, even numbers, are outside the circle. So this is a Venn diagram. Another example, let P be the set of prime numbers. A prime number is a number which is divisible by itself and 1 only, leaving no remainder. So our universal set Let me use a different color. So the universal set is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20. So we want to highlight all the odd numbers that we have. 0 is not an odd number. 1 is not an odd number. A prime number should be greater than 1. Another definition of a prime number is a prime number is a natural number greater than 1 that is not a product of two smaller natural numbers. So 0 is out. So we have 2. 2 is only divisible by 2 and 1. So 2 is a prime number. 3 is a prime number. 4 is not a prime number. 5 is a prime number. 7 is a prime number. 11 is a prime number. 13 is a prime number. 17 is a prime number. And 19 is a prime number. So again, we want to present this information on a Venn diagram. So we will put the prime numbers that we have highlighted inside P. So we have 2, 3, 5, 7, 11, 13, 17, and 19. So all the other numbers fall outside, but they are in the universal set. So this is our sign for the universal set. So all the other numbers which are not prime numbers, they fall outside, and these numbers are 0, 1, 4, 6, 8, 9, 10, 12, 14, 15, 16, 18, and 20. So this is the Venn diagram that we want. So now we have a new Venn diagram that we need to fill in. But to fill in a Venn diagram which looks like this one, we need to first consider the intersection of the odd numbers and the prime number. Then the elements that falls in the intersection will fall on this central region. So we'll put the intersection on this central region here that I'm shading. And as you can see from the graph, it's showing that the elements will be appearing in both A and P. So we need to consider the intersection of A and P. So let me put it here. Of O and P, sorry. So my odd numbers are 1, 3, 5, 7, 9, 11, 13, 15, 17, and 19. Then the prime numbers that I have, we have 2, 3, 5, 7, 11, 13, 17, and 19. So the intersection, odd numbers, intersection prime numbers, we have 3, 5, 7, 11, 13, 17, and 19. So these elements are going to fall into this region: 3, 5, 7, 11, 13, 17, and 19. So other odd numbers which are left, so we have 1, 3 is already here, 5 is already here, 7 is already here, we have 9, 11 is already here, 13 is already here, we have 15, 17 is already here, and 19 is already here. So other prime numbers which are not in the intersection, we have 2, 3 is here, 5 is here, 7 is here, 11 is here, 13 is here, 17 is here, 19 is here. So we only have 2. So the rest of the elements fall outside these 2 cells, but in the universal set. So the elements that I'm not seeing here, we have 0, 4, 6, 8, 10, 12, 14, 16, 18, and 20. So I'm supposed to be having 21 elements: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. So this is looking okay to me. So I've presented that information on a Venn diagram. Let's consider example number 5. If the universal set is numbers from 0 to 20, and E is the set of even numbers, and P is the set of prime numbers, use a Venn diagram to present this information. Okay, So U can also be used as a universal set. So our U is equals to 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20. So we want to do this one quickly. So U is the universal set. And we have this set. So these are even numbers, and here we have prime numbers. So I'm first going to highlight the prime numbers. We said the prime numbers with 2, 3, 5, 7, 11, 13, 17, and 19. These are our prime numbers, and of these prime numbers, the only even number that I have is 2. So I'm going to put 2 in the intersection, because the intersection of even numbers and prime numbers is a singleton, a set which only contains 2 as an element. So the other even numbers that I have 0, 4, 6, 8, 10, 12, 14, 16, 18, and 20. And on the other prime numbers, I have 3, 5, 7, 11, 13, 17, and 19. So I have presented the information very quickly on a Venn diagram. So the other elements which are not included in either E or P, we have 1, 9, 15, so let me count. Here I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. So I'm now done presenting the information on a Venn diagram. I was supposed to use this graph. So the next thing that we want to look at is complements. So again, we'll start by defining a complement. A complement of set A is the set which contains all elements that are not found in A, and it is denoted by A prime. So the example that we have is if the universal set is made up of numbers 1 to 10, and A is a set of multiples of 3, and B is a set of even numbers. So it means our A is equals to, A is a set of multiples of 3, so we have 3, 6, and 9. So A complement is a set of all the elements that are not found in A. So we have 1, 2, 4, 5, 7, 8, and 10. And B is the set of even numbers. So B is equals to 2, 4, 6, 8, 10. So B complement is equals to 1, 3, 5, 7, and 9. A union B is given by A is equals to, so we take A as it is, so it's 3, 6, 9. And B is 2, 4, 6. We are not going to include it because it's already in. And we have 8 and 10. Sorry, this is A union B. So the complement of A union B is A union B complement. This one is equals to 1, 5, 7, 1, 2, 3, 4, 5, 6, 7. 1, 2, 3. So that's okay. Our A intersection B is given by A intersection B is made up of, it's a singleton, 6. So the complement of A intersection B is given by 1, 2, 3, 4, 5, 7, 8, 9, and 10. So our A, we are looking now at E. So A is equals to 3, 6, 9. And B complement, let me look at B. It's odd numbers, 1, 3, 5, 7, and 9. So A union B complement is equals to 1, 3, 5, 6, 7, and 9. So the complement of A union B complement is equals to 2, 4, 8, and 10. So we have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. This looks okay. A complement We are looking at F. So A complement is equals to 1, 2, 4, 5, 7, 8, and 10. And B is equals to, B is a set of even numbers. So let me check. Yeah, B is a set of even numbers. So B is equals to 2, 4, 6, 8, 10. So the intersection of A complement intersection B is equal to 2, 4, 8, and 10. So the complement of A complement intersection B is equals to 1, 3, 5, 6, 7, and 9. I'll leave this one as your homework to represent the information on question 1 on a Venn diagram. Please like and subscribe my channel on YouTube. Thank you very much. Until next time, where we'll be looking at numbers. Cheers. And one thing before I go, mathematics is all about practice. You need to practice and practice and practice so that you get everything right. Mathematics is a subject which needs a lot of practice. So I encourage you to do all the exercises, and if you can, go and find other questions. You can do them, or you can share some with me so that we get to do and discuss some of the questions on the WhatsApp group. For those that want to join the WhatsApp group, send me a WhatsApp message on this number. You can send me a WhatsApp message or a text asking me to add you in the group, and I'll add you so that you get to join the discussions that we will be having. So until next time, cheers.